You can also just change the layout if you want only one screen.
I don't know whether that actually works because I'm mirroring my iPad to my computer. That's a new thing I'm trying.
Oh yeah,
And that's
then
why you don't see, like, it's not just using the iPad.
yeah, then maybe not.
And yeah, anyways, almost there. How many computers do you need for a single presentation? Depends on whether you're using Google Meet, then maybe a few. Oh no, the university wants to send me a push notification. Oh no. This is so great. Where's my phone? I don't have a phone. Where's my phone? The reason I want this computer because I don't know where my phone is. I know it wants to send me. Okay, let's see whether we can avoid that. Can you let me in? Or do I need to do it? Okay. Such a complicated thing. Fine. All right. Okay. You still hear me? All good? Yes. All right, so let's start. So I want to talk about next chapter, algorithmic stability and generalization. Fun stuff. So why do we care about this? I guess this is a bit weird because I'm looking at the screen of the other computer. This is the one that record. Okay. So why do we care about this? It's well, to recall what we were doing before. Maybe it's good to start with that. We were talking about these algorithms, a lot about ERM, but generally algorithms that take tuples and tuples of data, and then they return something. It's a loss function eventually. Maybe the loss is leaving 0, 1. They select a function and it has some underlying loss. And yeah, like they return this thing and some random data. And then we very quickly figured that you can get some bound on how well an algorithm like that is going to do on new data or in expectation. So in particular, just a simple application of Hövding's inequality with bounded losses gives that with probability 1 minus delta, the expected, so the loss on new data of the random selection of the algorithm can be upper bounded by the best possible loss plus some penalty, where the penalty depends on, in the simplest case, the coordinate of how many different choices we have. And it's log dependence and log 1 over data dependence and inverse dependence on the number of samples. And then we went on and generalized this by allowing ourselves to deal with infinite classes. So the loss class doesn't have to be finite, introduce various covering numbers, Rademacher complexity, and we generalize this bound by replacing this log coordinate with other quantities. And in all of this, somehow we are measuring how big this set is, this set G is, and these inequalities are going to depend on how big the set that we are starting with is. So now you might suspect that this may not be a very good fit to some algorithms. So the algorithm that we were looking at a lot is the ERM algorithm, and maybe it's not such a bad fit. We didn't talk about it, but you can show that in food generated these bounds are tied. So the log coordinate without any further structure really has to be there. The log covering numbers in some form, or metric entropy has to be there, or the Rademacher complexity. Some kind of penalty in the worst case needs to hold. But that's like for an adversarial choice of this algorithm, where it tries to make the deviation between the empirical means and the true means as large as possible. And of course, algorithms are not trying to do anything like that. The RM algorithm is not trying to do that. It wants to make just the loss small, the empirical loss. And as another example, you can consider something like gradient descent. So if you consider gradient descent, how does it look like? So some form of gradient descent could look like this. You have some weight vectors. They live in d-dimensional Euclidean space. And for each weight vector, there is a corresponding loss. Loss function. So this is loss function maps, elements of Z to the reals. And you can write what the empirical loss is. What is the empirical loss if you consider using some weight vector? The empirical loss is going to be, you take your sample, you plug in the sample into the loss functions parameterized by this weight. So that's the weight underlying the predictor, of course. And you take the average, that's your empirical loss. And one way to try to implement ERM would be to run gradient descent. So what does gradient descent do? Well, it takes the gradient of the loss with respect to the weight. This is hard to read. And so it takes the gradient of the loss, and it moves in the opposite direction of the gradient, right? So it's like the little figure that corresponds to this. It's like if you have some function, like let's say this function here, then if you pick a point, you can put the tangent line, and there is one direction with function grows, and the gradient is going to point into that direction. This is the gradient of the function at point x. And so the negative of the gradient allows you to slide down. So you try to slide down. You choose a step size, eta. So that's a positive parameter, step size. And you take your current weight and modify it by going against the current gradient, and that's the next weight vector. Okay, so in this case, everything is over this Euclidean space, so you're just like moving in the Euclidean space, and you try to find the minima. Of course, if the function has some nice structure, and this can work. If the function didn't have very nice structures, it's like really zigzaggy or whatnot, then this is just like, like trying to slide down and then can get stuck in local minima. But if the function would be nice, let's say it's a convex function and maybe it has some other nice properties, then this can come close to the minima of the loss. And then the algorithm would run for, I don't know, t updates. So j goes from 0 to t-1. And you take whatever the end result is, that's your weight, and that's what you're going to use for prediction. And you plug that in into the loss, and that's the loss of the algorithm. So now, some edge cases. So if eta is chosen to be 0, okay, this is initialized somehow. So to fully specify the algorithm, you have to specify and initialize it. One customary choice out of no good reason, but it's just like a simple choice, is to choose the weights to be 0. So whatever the initial choice is, if eta is 0, then of course, no matter how many updates you're doing, you're not doing anything. You start at 0, you stay at 0. And if you think about it, like this algorithm is just not going to use the full power of the set G. So a bound like this that talks about how big this G is kind of ridiculous, because the algorithm is not exploring the full set. It's staying in place. It's not doing anything. And by continuity, you can see that if eta is really small, then you also expect the algorithm not doing much. And in that case, of course, well, you can't really hope something like this. But if you just want to argue about how close the empirical mean is, sorry, the training loss is to the test loss, so the generalization error, and that's going to be small, right? Like you didn't do anything, you generalize well. It's basically a Hoeffding's inequality. You can in this case get rid of the log coordinate dependence. So if gn is just a constant, then of course this can be upper bounded by just square root log 1 over delta divided by n up to a constant factor. And the coordinate of G is gone, so there is life beyond bounds that depend on how big these sets are. And depending on what your algorithm does, you should be able to get better bounds than the bounds that just rely on how big this set is. Similarly, if you're running gradient descent, and you're running it only for a few steps, then you can expect much better channelization bounds. So, okay, so you get better channelization bounds. Do you also get good oracle inequalities? Well, for that, the algorithm would need to get lucky if it doesn't do much work to get close to the best possible empirical loss, which it will not do. So to get oracle inequalities, you have to consider the other side of the equation, which is, okay, how well does it optimize the empirical loss? But the point is that, okay, there are two sides of this. How close you are to the empirical minimizer, and then how well you generalize. And in terms of just generalization, algorithms that don't do much work should enjoy better generalization bounds than the worst case bounds. So the question is, how can you get something like that? So the name of the game is that you try to exploit specific properties of this map that maps the data to your predictor and eventually to a loss. Okay. So contrastive learning algorithms, as far as I know, they just use funky losses. So other than that, they're not too special. Yeah. So first, I'm asking a question about the contrastive losses, but I don't think that it's really that different than this case after you understand these losses that they are using, which is a little bit tricky, but can be done. Okay. So this was just the gradient descent, but of course people are running SGD, which is a randomized algorithm. In each round, SGD, unlike GD, which tries to calculate the gradient of the empirical loss, SGD just haphazardly picks one example out of, let's say, the IJ's example in round J, out of the n examples, and calculates the gradient against the loss on that example, given the current weight, and makes a move. So this is our first encounter with a randomized algorithm. So the SGD, even if you fix the data, is going to, like different runs, it returns different answers. It depends on how long you're running it, right? So it's still, it is random, but it's kind of a discrete-ish random thing. It depends on in what order it's picking the examples and so on and so forth of what weights it can get to. And there are all these weights that it can get to, and it puts a probability distribution on it. So that's what SGD does. And in the analysis, sometimes you use randomization to kind of control generalization. If you randomize more, if you start to add a lot of noise, for example, so another choice here would be to, I don't know, add some big noise. So epsilon J is Gaussian noise. If you add a lot of noise, then you just get random walk. Then the algorithm, what is it doing? It's not paying attention to the data. It should enjoy an extremely good generalization bound. Is it going to be a good algorithm altogether? Well, it depends on whether it also succeeds in paying attention to the data to some degree. So of course, with large noise, it's not, but yeah, there is a trade-off then that you can play with. Anyway, so there are all these choices that you can make. and you get all these different variations of these algorithms. And analyzing these algorithms in terms of like what ERM would do, or like what's the worst case, seems to be missing the point that these algorithms do have these design parameters that control how well they're gonna generalize. So that's very clear. So you expect to see generalization bounds, at least for these algorithms, that reflect this. And currently we don't have any tools for that. So today we're looking at this algorithmic stability idea and how it can be used to get such bounds. Okay, so what is this? Algorithmic stability. Yes.
Are the losses still bounded here?
The losses are not going to be bounded. I just made them bounded here for the first inequality, so I can just use things. But yeah.
But then when we are talking about this small eta, like smallness shouldn't it be like scale dependent?
Well, if you have, this convex situation, so this map from the weights to the losses are pointwise convex, let's say, then what matters in choosing eta is the smoothness of this loss. If it has better smoothness, you can use a higher step size. If it has worse smoothness, you have to use a smaller step size. That's kind of an optimization concern. So here we will not care about this. We will only care about analyzing the generalization abilities of the algorithm, whatever eta it uses, right? So there are two concerns. Like you want an algorithm that generalizes, and you want an algorithm that optimizes as well. And you separate the two concerns. So today we are not talking about optimization.
And why can't we apply all the previous analysis to SGD?
So you would need to then get some capacity measure for this loss set. And if you get a capacity measure, sometimes you can, because maybe the W lives in a bounded set, or we talked about this, right? So in classification, maybe it's only the direction of W matters. It doesn't matter how big it is. Then you can get a capacity-based bound. But the problem is that it doesn't reflect correctly that like how well actually the algorithm is going to generalize. As I said, if you choose eta equals 0, then I expect the generalization bound to be excellent. It should tell me that you're generalizing as well as something that's not learning. It's like a Hovding's inequality or Bernstein or whatever, right? Whichever inequality you choose, right? So you're not paying any price for the size of set G. Okay, so we want bounds that do not pay a price for the size of G, because these algorithms are, if you have an algorithm that doesn't effectively explore G, it seems unnecessary to start to argue about how big G is, right? Does it make sense?
Yeah, thanks.
Okay. All right, so we're gonna take the properties of this map into account, and we do this using stability. Okay. And well, this is going to be very familiar for Kushaksha. Having worked on differential privacy. So how does this work? So you take the n-tuples over the set Z, and we introduce this distance function, the Hamming distance function, that takes two n-tuples and counts how many coordinates they are the same or they are different. It's like you have Z1 to Zn, you write it down, You write down below it the other guy, okay? And then you just like look at, are they the same? If they are the same, then no cost. And then, oh, these are different, then there is a cost. So you create all these indicators, you sum them up, and there comes the Hamming distance between these two antapos. Okay, so that's the Hamming distance. And so we're going to call an algorithm that maps antapos over the set Z to functions, epsilon uniformly stable. So that's what we are defining. If for any two antapos which are within a Hamming distance of 1 to each other, so that's like they only differ in one position, first, second, nth, it doesn't matter. If you look at what the algorithm does, it doesn't change much its output. Okay, so this is the output of the algorithm when the input is Z, one antapo, one sample, and this is the output on another sample Z prime. And you look at the difference. It's the pointwise maximum difference. It's like these are loss functions. So they map, the space Z to reals. And you look at the L infinity difference. It's like a loss function, how different they are. So in other words, we say, this is the equivalent definition, we say that an algorithm A is epsilon uniformly stable if it's epsilon Lipschitz, where you equipped your input space with the Hamming distance, and the output space you equipped with the maximum norm distance. Okay, so it's just a form of Lipschitzness. Input doesn't change too much. Output doesn't change too much. Okay, seems like a very, very strong notion. And it is indeed a very strong notion. Right? So for example, if the losses are all binary, then requiring that no matter how you change the input, the output doesn't change at any point. That means, well, within epsilon, where epsilon is, let's say, less than 1, so that means that this is a constant function. So we're going to run into trouble if we try to apply this to binary classification, right? Right? Because for binary classification, this is either 0 or 1. This is either 0 or 1. If they are the same, it's okay. They're within epsilon. If they're different, and epsilon was less than 1, and this inequality doesn't hold, so they have to be the same. So this means that for any two inputs that differ at one position, they have to be the same. And then for any two, you can walk, like one by one, changing the first to the last in n steps. You can do that, and you get that this thing has to be constant, right? So not for binary loss spaces, right? So for binary loss spaces, this is absolutely boring. So too strong. But there are relaxations of it, and then people study that. Today, we're not studying that. Because this is good enough, and it's going to be quite interesting to see how far you can push this. Okay, so so this was for algorithms which are not randomizing. So you take the sample, and the algorithm returns its hypothesis, prediction, whatnot. You plug it into loss, it becomes a loss function, deterministic loss function, given the sample. If the algorithm is doing any randomization, then you can think about, and you should be thinking about the algorithm as a probability kernel. So that's the form. So the probability kernel is going to take an n tuple and returns a distribution over hypothesis. And after plugging into losses, of course, it becomes a distribution over loss functions. And so you can think about this as just a transition kernel, where you're transitioning from a sample to a randomly chosen loss. Okay, so I write this. So K dg d of g given z1, and it's like usual notation for probability kernels. And if you have such a probability kernel, then okay, you can take the mean of the functions. And how do you do that? Well, you can integrate. Actually, this should be pointwise integration. So it's like, let me clarify. So here, the z is in Zn, so that's an n tuple. And then I guess you can choose a z prime, where z prime lives in z, and then integrate with respect to the probability distribution. So K chooses, given this n tuple, the sample, it chooses a probability distribution over these functions. So you can integrate over this probability distribution of whatever value those functions take at whatever input z prime. And that gives you some value, some expected value, expected loss, if you're randomly choosing according to K. And you can just give it a name. So I give it a name of mu of K. Mu stands for mean. So that's why I use mu. So this is the mean function associated with this probability kernel K. And then the definition would say that this randomized algorithm is epsilon uniformly stable if mu K, this deterministic map, so mu K maps sample to just a function that maps values of z to reals. So if this mu K is epsilon uniform stable, so it's basically take the mean map. If the mean map is epsilon uniformly stable, then we call the probability kernel, this randomized algorithm, epsilon uniformly stable as well. And the idea is that, of course, if you want to reason about the expected loss that is going to be suffered by the randomly chosen hypothesis and eventually loss by the algorithm, and you're content with just thinking about the expected loss with respect to this randomization that comes from the algorithm, then it's enough to study just the mean map. So in a way, it's somehow, yeah, not too. Yeah, go ahead, try.
Just for people who don't understand what is a probability kernel, can we just view this K as a conditional probability?
Yeah, that's the same thing. Probability kernel would have some extra properties, like a Markov kernel, but it is just for, yeah, like as I wrote here. So this gives you the gist, right? Like for every sample, you get a distribution. That's it. You can call it a conditional distribution, conditional on what the sample is. What is my distribution over this other space? Yeah.
Okay, so
But
this
it's
mu
basically
k is
just
the
a map. It's a random map, right? Like, or like it takes the input and then it returns a distribution. So a lot of times people call this a random function, because it's like you can then sample from the distribution, right? And then that would be a random choice according to this case.
All right, so mu k is just the conditional expectation. That's the reason why it is a function.
That's right. So if you would write k, g is sampled. Oops. G is sampled from k given some z. Okay, so you feed some z, you sample from k, you take its expected value. That's what I call mu of k.
So
At
this
z.
is essentially just
At z.
generalizing the above epsilon stable notion as like taking the expectation
Right,
over
right.
this a of z.
Just talking
Okay.
about the expectation, and that we do that because it allows us to talk about, you know, an expectation over the randomization of the algorithm. What does this algorithm do? Like, is it going to generalize on expectation? What it doesn't allow you to do is to also talk about the variance that's induced by this algorithm. So if an algorithm is randomizing, then maybe you care about how frequently it's going to get you a good answer, not only whether on average it gives you a good answer. And if you know, like right away, just take the mean, then of course, like all the other properties of the distribution are gone. You reduced it to just the mean. So it's like a first cut. It's good for that. All right.
All right, I'm done.
Okay. All right. So first result, I think maybe it's too much to call this a theorem. Let me call it a proposition. It's a small observation. So you choose a distribution over your space Z. You choose an epsilon uniformly stable algorithm or kernel, and then choose a sample from an IID sample of length n from this distribution P. Then choose a random loss according to K. And as usual, we have Pn, which is the empirical probability measure associated with P based on the sample Z. And then it holds that the expected loss is upper bounded by the expected empirical loss plus epsilon. Okay. So here I have some little note about this notation. So the expected loss is of course equal to the expectation star rule, the expectation of the expected loss given the sample, and P, they just like integration. So you can move that outside of the expectation. So you move it outside of the expectation. There's nothing random there. That's just an integral. And then you end up with this. And what is this? Well, this was denoted by mu k of z, right? Like this was the mean at z. And so it just, because later I'm going to use this alternate notation. In all these things, when we're talking about these randomized algorithms, like you you can just think about that. Well, this algorithm is like, just replace it with the mean function, right? Like, it doesn't matter. It's just mu k. Like, we are reasoning about mu k anyways. And in terms of the expected loss, the random choice has the same expected loss as the non-random mean choice. Of course, it's just a time.
We can take the P out because of Fubini.
Yes.
Okay.
Yeah, when you're changing order of integration, of course, it's Fubini, Tonelli, and whoever else needs to be mentioned. Okay.
Yes. Sorry, forgot Tonelli.
Yeah, I don't know. Tonelli is probably turning, by being dead. Okay. In his grave, right? Okay, so how do we prove this? So let's take another sample of length n that's independent of our sample and g. Okay, as usual, let's take the underlying empirical measure, and we're going to do something funky here. So we did something similar with considering symmetrization, right? So we replace, we take the original sample and just replace the ice component of that sample with the ice component of the new sample, of the prime sample. So this is what I denote by Z upper index I, superscript I. And so this is my Z superscript I, and then of course I can sample a new loss from my random kernel given this new sample. So now notice that the joint distribution of Zi and Gi is the same as the joint distribution of Z1 prime and G. Right? It's why? It's because before that you can notice that the joint distribution of Zi, Z subscript I, and Zi is the same as the joint distribution of Z and Z1 prime, right? Because it just this independence, like this is the a sample of length n+1, and all the components are independent of each other, and it doesn't matter how I call them. And because of this, it also holds, of course, that like this equality holds. And so once you notice this, then you can write the expected loss. Well, of course, it's the expected loss on a new sample. So G is the random loss function that we end up using. So you can plug in an independent sample into it and then take that expectation, the graded expectation. And now, noticing that this distribution is the same as this distribution, you can replace G and Z1 prime with Gi and Zi. Okay. So because of this, so you can do this for all the indices I, ranging from 1 to n. You can take the average, and you have that the expected loss is just the average of all these losses. And so now, okay, we can write the difference between the expected loss and the expected empirical loss as, so the expected loss can be written this way, so that's here. And the expected empirical loss. So what was the expected empirical loss? So that's not here, but the P and G is just, you have the G's and you plug in the ZIs. So it's just the average of the losses at the sample. And so that gives you this second term here. And then you can use the TAR rule and take the conditional expectation of this difference inside given Z and Z prime. So that just integrates over the randomness of the algorithm. So in particular, if you take the conditional expectation of GI ZI given Z and Z prime, that just mu of k at ZI, Z subscript I, and if you take, because G of I was what? G of I was using this sample, right? So Z subscript I. And here we're just calculating the mean. So that's exactly mu. And the same with G and ZI. You just get the mean. And now if you just take a look at the inside expectation, take maybe absolute value, then this inside expectation is the difference between these two guys. And by assumption, the difference between these two guys is less than or equal to epsilon. So all of these terms are less than or equal to epsilon, so their average is less than or equal to epsilon. We're done. Just symmetry. It's almost a tautology, right? It's like we did very little here, if anything. Okay. So that's the first observation, that if you have this epsilon uniformly stable algorithms, then that also means that their grand expected loss is upper bounded by the expected empirical loss plus this little padding of epsilon. Of course, like this epsilon uniform stability is very, very strong notion, so it's not really that surprising. But it somehow shows that maybe this is a good way of thinking about what's happening between with the generalization error. So this is like, the useful side of the generalization error, useful direction of generalization error bonds. Okay, but you might ask, okay, this is great, but this only gives you control over the expected losses. How about high probability upper bounds? So for this, we have another result. This is this result. So it says the following. So let K be an epsilon uniformly stable algorithm. Choose a sample of size 2n, IID from some distribution P. Alpha is a value between 0 and 1. And choose a data and assume, okay, so assume actually that for every data, just need it for data over 2, but that this inequality holds. So what is this? So there is an alpha, so that's should be familiar from what is playing around with multiplicative Chanov. Maybe it's just going to be 1. So there is the mean loss of K, and the mean loss of K should be upper bounded by the empirical loss of K at a new sample plus some error term that can depend on data. So notice that this is independent of this, right? So the sample underlying Pn prime is independent of the sample that goes into this randomized algorithm UK or K. So that means that for this, you can just use a Hoeffding's inequality. Let's say all the losses are bounded between 0 and 1. then this an inequality like this is going to follow from Hövding's, and in particular, so note if I don't know everything here, so mu k is in the 0-1 interval, then epsilon and delta can be chosen to be square root log 1 over delta over n. Yes, Shuai.
I'm confused about what this P mu kz is. It is a little bit hard for me to
Which one?
interpret this.
The first or the second? This?
Anyone. Like, I just don't know where this z is from.
Okay, so the way to parse this is as follows. So maybe forget about that this was a randomized algorithm. You just have an algorithm, mu k. It takes an n-tuple, and it returns a loss. So now you have a loss. So this is a function from the space Z to reals. So you can integrate it. So that's P.
Oh, okay.
So P is integrating this loss. It gives you the expected loss. It's like the test loss. Call it test loss. So it's like P of mu k Z, so that's the test loss. So there is still randomness here because Z was random. So that's why you have the outside expectation that takes away that randomness. Okay? And okay. And on the other side, you have the same story, right? So this mu kz is just this a function from Z to R, and you take its empirical mean with respect to Z prime, the shadow sample. Okay.
Why do you have this alpha here?
In some applications, it's useful. It's at the moment it's like unclear, but just for generality, to mess with you a little bit. Yeah. So if you can choose alpha equals 1, it's great. But let's say you want to get, I don't know, this multiplicative chain of like, use the variance tricks, Bernstein's inequality, or multiplicative chain of, then it's better to have the alpha. Okay. So anyway, so this is the condition. But as I say, this is like a very benign condition because it just says that grand mean is upper bounded by empirical mean plus some error term. It's like concentration of measure, concentration of averages in particular. So yeah, there is a question about whether K could be SGD. Yes, K is SGD. It could be doing mini batching, stuff like that. That's right. Okay. Yeah, I didn't talk about the mini batching because it's just a variation. It doesn't add much from the perspective of this analysis. I mean, it doesn't make the analysis harder. It makes it more involved to write. But
How do we-
same steps go through.
Sorry, how do we know that SGD is epsilon uniform stable?
We don't know yet.
Oh,
It's
okay.
like that requires some arguments. Is it like, yeah. It's yeah. If you're thinking about it, it's like, do you expect gradient descent to be stable? Okay, that's maybe the first question to think about. If you have some nice laws, then maybe. So you're placing, you have n observations, you're replacing one of them, then the empirical loss becomes a different empirical loss because you replaced one observation. So yeah, maybe. Okay, why isn't an expectation on the right-hand side? Yeah, it's because we want a high probability bound. We actually want to get rid of some expectations. So we want to bound the yeah, I think I have a mistake here. So there's no expectation here. So we want to bound the random test error with high probability. So the form of the result is going to be as shown here. Okay, let's parse it. It's quite long. So this is the test error. So you take your algorithm, you run it on the sample, the random sample, and you take its test error. Okay. And the test error is upper bounded by the empirical error of the algorithm, which you can measure. So that's kind of like what we like. Plus some term. Okay, so if alpha is not 1, then this is annoying because this is like the empirical. Oops. This is like the empirical loss, but here you're taking expectations. It's like, I wish that was not there. So this is most useful when alpha equals 1. If alpha equals 1, then okay, like this term is gone, happy. Right, that's the beautiful bound. For some reason, sometimes alpha smaller than 1 is, but then you have to deal with some of this. Okay, and then we have the error term that comes from this assumption, but at that over 2 because we are taking a union bound, and you have another term that has a log 2 over data in it, but not under the square root, and that's scaled with epsilon. Okay, so that's kind of interesting. So the tail behavior of the test loss is governed by, okay, like the empirical thing, and then maybe this is not there, plus some concentration term that comes from just comparing means with empirical means. It's kind of a Hovding thing. And another term, which is slightly bigger than what you would expect from Hovding, where you would have like square root log 2 over data. So there's like a sub-exponential term, slower decay with data going to 0. And this is what's scaled with epsilon. And epsilon appears without data once more, and it's just multiplied by this 3 minus alpha, so it's like 2 epsilon, 2 extra epsilons. So if you make your algorithm stable, then you're decreasing these terms, and you can have this high probability bounds. Okay. So this is the result that we are after. Good. Okay. So for the result, to prove the result, we use a lemma which don't prove. The proof of the lemma relies on some other result, which is like what I call an exponential Efronstein inequality, which is kind of a very nice concentration inequality. But it's a bit beyond what we can cover in the class. So we just like take this lemma granted. It's kind of an interesting lemma. If you're interested in the proof of this, it's in the book. And if you're interested in the proof of exponential Efronstein, then there is the concentration inequalities book of Boucheron, Massard, and Lugosi. It's in there, or it's in the original paper that is also cited by Dong. Okay, so what does this lemma say? So the lemma is talking about, finally, okay, we got rid of the randomizing nature of the algorithm, and you just have, some map that maps n tuples to these losses, and you assume it's epsilon uniformly stable, and you assume that it's centered with respect to this p. Okay, so if you had a map, it was not centered, you kind of like subtract the mean, and then it will be centered, and that's how we are going to use this anyways. So there's this centered map, and we assume it's epsilon uniformly stable, and then define this other type of centering, or leave one out centering, or something like that. So how does this work? You take an n+1 tuple, and you look at what G gives you. When you take that n+1 tuple and you swap the i's coordinate in it with z n+1. Okay, so that's your z subscript I now. So z n+1 goes in there. And you look at the result, and okay, so I didn't use this notation, so I don't need to do that. So this is a function, and then you have this function at the value of zi. So what is that? That's the value that was left out at this position. So it's like a leave one out thing. So people familiar with leave one out estimation, right? So that's the idea, that you are running your algorithm by leaving out one example in your training sample and then testing against that. And then you do this by rotating over all the examples in your training set and take the sample mean. This is an unbiased estimate of the loss of the algorithm that uses one less examples. But here we are doing something different, because we can imagine we have n+1 example, so we plug in zn+1. But it's kind of the same thing as the leave one out estimation. So this is like leave one out estimate, and it's centered. So it's the centered leave one out loss estimate. Okay. And so how is the centering? Well, the centering just says that, okay, by the way, so because it's too much to write this many parentheses, I also use the notation that this value is the same as this. It's like just use a semicolon. Okay. So here I'm using the semicolon in this second part. And this function is still evaluated at z of I, but taking the expectation with respect to these guys. Okay, so the zi is not there, so it's like literally just taking the expectation over the z subscript I, just written in an integral form so that it's clear what it is. Okay. So the result says, this lemma says that for every delta with productive 1 minus delta, the centered leave one out loss estimate cannot be too large. It's some log term. So somehow n is creeping in. We have seen similar things, but it was under the square root log n. Sometimes it appears. Sign of some unibounds. And the epsilon uniform stability constant and the log 1 over data term. So there is concentration of the center Levin-out estimate around 0, and it's governed by how stable the underlying map is. So it's perhaps not surprising that if you have a stable map, then these Levin-out estimates are sensible. And here, actually, I wanted to notice that people are using, in practice, Levin-out estimation or cross-validation and whatnot. And when they are using these, I think that they should be thinking about stability. Because for two reasons. So first of all, you want to know when Levin-out estimate or a cross-validation estimate is centered around its own mean, is there concentration happening? So in this lemma, we see that if you had a stable algorithm, concentration would happen. The other reason you should think about whether stability is happening is because in these estimates, you're trying to estimate the performance of your algorithm at the sample, but you're running the algorithm on a modified sample where you're leaving out something like one block is left out in cross-validation and so on and so forth. So it's like, how is that even related to the output the algorithm is going to produce at a sample? If you didn't have a stable algorithm to start with, this would not make any sense. And somehow it's also a family of algorithms. So it's like, because a lot of times it's like you're reducing the size of the sample, right? Like you want to know how well your algorithm is going to perform where you had a sample size of n, and you do leave one out estimation. Then you're leaving out one. So then, okay, you're measuring performance of the algorithm, whatever that means, right? Normally, you define the algorithm for a fixed sample size, but of course, like we do have an idea about that. Oh, like if the sample size was different, it's still kind of the same algorithm, right? But like, does it need to be? Yes, it better be, because if it was not, then these leave one out estimates and cross-validation and any of this would not make any sense, right? But this is about stability, right? Like if I remove an example from my training set, how much is are my losses shifting around? So both cross-validation and leave one out estimation make sense only if you're talking about stable algorithms. So this is another reason why it's worthwhile to talk about stability. And people wonder a lot about like, oh, is like, do I get a good estimate using cross-validation or any of these other things? Yeah, they should be wondering about whether their algorithm is stable or not, because it's going to depend on that mainly. Okay.
But like when this cross validation is introduced earlier, like in earlier courses, you never talk about stability of the algorithms.
Yeah.
Yeah.
It's yeah.
So, so is it like is it necessary? Like
It
if you're
is
doing cross,
necessary, because if you think about, like, if I run a neural network, if your sample size is 10, and if I run, I don't know, an SVM where the sample size is 9, and you run leave one out cross-validation to try to measure the performance of the neural network at the sample size of 10, it will not make any sense. Do you understand?
yeah.
Right? It's like in all of these courses, when people, I guess, like intuitively, implicitly, it is assumed that the algorithm is going to be stable. But it's never granted. And actually, a lot of the algorithms might be very unstable. And if you have an unstable algorithm, don't expect these methods to work well. And some algorithms are more stable than others. So, yeah. I guess it's in practice, it's not causing trouble because people are not adversarially using these methods. But if you want to know whether you have a chance of using the cross-validated estimate or whatnot to get good estimates, then it's really about the stability of the algorithm. So I think I wish in the introductory machine learning courses and books, people talked a little bit about stability when it comes to introducing cross-validation, for example. Because it just makes zero sense otherwise. Yeah.
Sorry, yeah, I think what I understood, it's something like the algorithm shouldn't be very sensitive when we go from, for example, n+1 samples to n samples, right? This
Yeah.
is the meaning of stability.
Meaning, yeah.
Well, yeah.
Or n to n+1, or you place one sample with another, and like just small changes to what the input to the algorithm is shouldn't cause a big change in what the predictor, the algorithm drives in terms of the loss. Like we don't care about the hypothesis might move. Like you can have very different weights, let's say in the neural network, but if it's the same loss, it's all good.
Yeah, but I think the value of and how big is the n, I think it's also important, right? Because I mean the large n, maybe.
Right. I mean, you expect algorithms, vacuum algorithms, to be more stable as the sample size grows. So it's like, for example, if you look at this result, so here, normally we expect like a 1/√n behavior, right? Like there is the mean. Sorry, there is the random test error compared to the empirical error. Let's say this is not there. And some concentration is usually happening. So you have like this 1/√n type of terms. And here you have these epsilon terms. And so if epsilon is of the order of 1/√10, then you kind of get back the usual behavior. But if epsilon was much, much bigger than 1/√10, then you get something worse. If epsilon is much smaller, then you get something better. So it's kind of now it's decoupled, but as n gets large, for a good algorithm, you expect epsilon to behave like this or better. If it's not even behaving like this, then it's like, well, what is it doing?
Yeah, we have some expectation over the epsilon depending on the n. And if it's, for example, we have a larger epsilon, we can say, okay, it's not stable.
Yeah.
Something like
that. So epsilon is really the insensitivity of the algorithm. It's like the larger the epsilon, the worse the algorithm is from the perspective of generalization. And then that shouldn't be confused with like how good the algorithm is. So generalization is important, let's say, if you want to use the training sample to derive conclusions about the test performance, right? Like that's the obvious use of generalization. So here you're measuring performance on the training set, and then you try to derive conclusions about the test performance. But that's not everything about an algorithm. As we talked about, it's like a double-edged sword. Because if you have an algorithm which is very stable, that means that it's not reacting to the data. But of course, you want algorithms to react to the data. So it's like they are fighting against each other, right? So you want sensitivity, so that if something is expressed in the data, then you get it out. So complete insensitivity to the data is not a good thing. Super sensitivity to the data might not be a good thing, because then it's kind of hard to believe that the algorithm is going to do well. There's no proof here, or like it doesn't flow from any of the inequalities I'm showing you, but the algorithms are trying to minimize the empirical error, right? So this guy here. So if you have an algorithm that is trying to do that, and it is very unstable, then what the heck is it doing? Then it's not really confining how well the test error, like how big the test error is going to be. So at the end of the day, you kind of need both. Anyways, all right, let's see the proof. Well, I don't have much time. The proof is not super interesting, I wouldn't say. I mean, it's just some algebra and like pushing terms around. I just share this, and then you can read the proof if you want to. Yeah, there is really nothing much. It's just chaining some inequalities and pushing terms around. Is there something? Okay, so there are some little things like you need to define this G, and okay, it should be centered. So you just center it like, okay, yeah, that's and then if you centered it, then it's not epsilon uniform stable, but 2 epsilon uniform stable, and things like that. But apart from that, it's just like just some easy algebra. Okay, I think that I stop here. So the next time we should talk about SGD and why is it stable? How is it stable, and what do we get from all of this for the SGD analysis? Is there some lesson? Okay. All right. So in a nutshell, I think what was important is that stability is good for generalization. It's also good if you're using leave one out and cross-validation. And those are 2 good uses. And this notion of stability is just like one possibility. It's a strong notion, but this is the notion that gives you the ability to prove a high probability result like this. So there are other notions, and for those other notions, it's I don't think that we have comparable results. It doesn't mean that we can't have, but like we just don't. All right. Okay. Okay, there is a question. Can we say that tail inequality? Do you want to ask your question? Sadek?
Yeah. Can you hear me right now?
Yeah.
I mean that the tail inequality that you proved for this K, random K, I think it should have tighter bond in case we have a mini-batch gradient compared to when we have a stochastic gradient descent. It's some kind of intuitively, I think. Can we prove this somehow?
So why do you think so?
Because stochastic gradient descent has more somehow randomness compared to mini batch.
Okay, so adding more randomness, does it make the algorithm more stable or less stable?
I think it makes it less stable.
Is that really true? I would think that adding noise kind of
It's good for generalization.
washes out signal. So adding noise fights against jumping on, information that's there. If I add a lot of noise to my algorithm, then it cannot be too sensitive. Don't you think that that could be the case?
Yeah, maybe.
Yeah, so I would think that it actually works the other way around. So if you're running mini batch, the extreme case of mini batch would be just gradient descent. And okay, gradient descent is going to be stable as well, but it might be less stable than if you start to add a lot of noise. And one of the algorithms that's also discussed in the book is SGD when people add Gaussian noise here. Stochastic launch one, whatever. It's just like adding extra noise. And that makes the algorithm even more stable. It's kind of interesting. And actually, if you add noise of the right magnitude and you run this algorithm, then you can show that, like, interesting things about it. So if you scale things absolutely right and you run the algorithm indefinitely, it's going to sample from what's called the Gibbs distribution. So it has a stationary distribution. So all these algorithms are randomized algorithms. They're like, okay, given a weight, what's the distribution over the next weight? Given a weight, what's the distribution? Like just applying this over and over again. It's like moving with a Markov chain or like a random walk, but it's like a directed random walk for the weight space. And if your conditions are right, let's say you're bounded weight space, whatnot, then you can have a stationary distribution for the resulting Markov chain. You might be converging to that stationary distribution, and that's a whole interesting story that now you can start to think about, if I want to, okay, so I can design algorithms by just thinking about what distribution I want to choose. And what distribution should I choose? So one of the distributions is just this called the Gibbs distribution. It's basically take the empirical loss, exponentiate the negative of the empirical loss with multiplied with some constant, and sample from that. So yeah, that's the Gibbs distribution, and interestingly, this algorithm. This SGD algorithm with this added noise can kind of emulate that. And now you can think about, okay, is the Gibbs distribution like a stable choice? And that's going to depend on this parameter. So you take the empirical loss, multiply it, so scale it up, losses become big. Then you take the negative and exponentiate. So that means that you're going to jump to the minimum if you're sampling from this distribution, because you are like scaled up things very harshly. It converges to Dirac data if the scaling constant goes to infinity. But well, okay, assuming that there is a unique optimum to the empirical loss. And of course, the ERM algorithm is not necessarily stable. It depends on whether the losses are nice. If the losses are nice, okay, so that's another discussion. Then even ERM is stable. And then you can analyze ERM by just using stability. It's kind of, that's also neat. But if the losses are not so nice, then ERM might not be stable. It might be sensitive. And then in Gibbs, you don't want to use this big constant. you know this Gibbs distribution business, right? Like physicists would call the inverse of this parameter the temperature, right? Like high temperature, then like your system is everywhere. You're basically randomly generating an output. You don't pay attention to the loss. Low temperature, you're kind of freezing the system, and you go to the minimum of the loss. Anyways. Okay, Roshan?
Yeah, so I had I don't know if this is connected to what you were saying, but here we had this very strong definition of sensitivity, right? Like we can just take one data point from the input and change it to any other Z, and then we're looking at how the output changes. But here, like Leeuwenhout or whatever, there's this other notion where we replace one point with another point drawn from the same distribution as all other data points, right? And that could, like, you can have an algorithm, for example, let's say you have a magical algorithm that just detects the pattern in the data, right? So the data is coming from some family of distributions parameterized by some parameter, and it just detects what that parameter is, right? So for example, it detects the coefficients of a polynomial that fits all the data, right? And now if you replace one of the points by just some arbitrary other point, the algorithm could be very unstable. But if you replace it with another point that's drawn from the same polynomial that fits all the remaining points, right, then maybe that same algorithm could be considered stable, right? So is this is that important here, or are we not losing much by having such a strong?
I think we are losing a lot. I agree with you. And actually, I tried to write a paper a while back where we were using a refined notion of stability that was paying attention to unexpectation, how much things change. So it's like, this is like an L-infinity norm stability notion, and then you can get LQ norm stability notions.
Right, and we have L-infinity norm on the output, the loss function, but then we can also use some more.
Yeah. So I'm not even talking about that. You can keep that L-infinity, but on the input, we also had kind of a supremum over all possible, Zs and their changes. Right. And it's not respecting the input distribution. So yeah, like if you had a good distribution, so the instance dependency of the algorithms is also lost, right? Like it became a worst case concept. This epsilon uniform stability is worst case, both in terms of the responses, the outputs, and both in terms of the inputs.
Yeah. Okay, and that makes sense. So if you do have if you just sort of think of this naively, then this stability versus sensitivity is just like a straightforward trade-off, and it seems like you just have to do something silly. But if you have like a more subtle notion of sensitivity, then maybe you can actually get improved stability and sensitivity by sort of having a clever algorithm that detects patterns or something.
Right. Yeah.
Okay. Yeah.
So this conservative notion of stability becomes extremely unhelpful in various examples. It just becomes a bottleneck. So you see that the algorithm, maybe through other analysis, you know that this is a good algorithm, but this analysis, because the notion was very conservative, is not giving you good result.
Yeah, makes sense.
It does happen.
Yeah.
Okay. Yeah, if anyone cares about that, there's that paper, and then there's work to be done. It's a little bit late for the projects, but all right. Okay. Other questions? No other questions, then that's it. Right? Cheers.
Thanks.
Climbing time.
Yeah. Don't break my heart.
See you on Thursday.
Yeah. See you.